So it's a real pleasure to have with us Alicia Sintes Olives from Universidad de las Islas Baleares. Alicia is an old friend of the house. She's been here many times. Actually, we have a recording together up in the common room. She has worked on gravitational waves all her life. Essentially, it was one of the few groups in Spain to initiate research in gravitational waves. Others like us have more newcomers into it, but she's been there for 30 years. I mean, really long time. She's a member of the LIGO collaboration, participated personally with the students in the first detection of gravitational waves done by mankind. I think it's a great achievement. It's something which has been recognized, with the Nobel Prize. And I think it's a great pleasure to have someone of her stature describing what she's doing nowadays to learn more about the universe with gravitational waves. So without more ado, I introduce her and you take the floor. Thanks for that.
Thanks, Juan, and also thank you for inviting me. I know it was hard to get me here because I'm not the most easygoing one. And it's a pleasure, as Juan said, to be here again after the pandemic once more. Be here in this building. I see many new faces. Well, I still see some old friends, but and well, as I said in the abstract, I'm going basically to overview a bit what were the latest results from the last science run and about these new detections and so on. But well, and then I will continue with my topic, or my main topic of research of these last years, that is to hunt for continuous gravitational waves, and then explain you why these boring ones are also very interesting, why are they challenging to find, and the kind of problems we are analyzing. Then you can tell me when you are already tired, because I have too many slides. I will try to go fast, and then you can ask me questions of whatever you think is more interesting. I apologize because I just put the material from different talks in one into a little mess, as I usually do, and let's see what happens. So as you know, the scientists from LIGO and Virgo basically initiated a new area in astronomy, basically almost 7 years ago, with the first observation of the gravitational wave detectors, of gravitational waves for the first time. That was the 14th of September 2015, and this was thanks to these cathedrals of science, these new observatories that have an amazing sensitivity. So these are the most sensitive optical devices that the men have ever constructed in the world. And this first discovery happened, as we also know, exactly 1 century after Einstein presented his new theory of gravity. It has been a full century. There many things have been going on. I will not enter into these discussions. In the late 80s, there were the first detectors, but there were some claims there. Of course, you might have heard many stories. And between 2002 and 2010, that was the first, the initial era of the gravitational wave networks of these initial detectors. They didn't see a thing, but basically they proved the concepts that these machines can work, that they will be achieving the desired sensitivity. Then there were the grades, and the day in which the LIGO first light into the laser beams, blam, first detection, exactly on that day. 2 years later, was fantastic as well. Then there was the European detector Virgo that joined the network, and many beautiful things happened in this last month of coincidence together. Even this other breakthrough in which we could start multi-messenger observations. Then there were explosions of many prizes, and then during the last science run, another detector has been joining. There's plenty of stories. So we are no longer talking about science fiction. We have a full network of gravitational wave detectors all around the globe. It's a growing network that is currently consisting of the 2 LIGO detectors separated 3,000 kilometers away from each other in Livingston and in Hartford. In Pisa, in Italy, we have Virgo. This is a bit shorter arms, 3 kilometers arm length. Then there is the small GEO600 detectors in Germany. Now it's basically like a test facility, but usually it's always in Astrowatch mode, where basically all the technology of these big monsters has been basically developed and tested in this detector before put into the big ones. And then we have KAGRA, 3 kilometers underground, basically is trying the technology of 3rd generation detectors. Still is far away from the sensitivity of the other big ones, but we'll continue. And now there is under construction LIGO India that I hope that this will be started operating in 2025. So we have these growing networks of detectors, and at the same time, this is a beautiful emerging field of research, and there is a growing number of groups all around the globe, in particular in Spain. So there is now, I would say, quite well-established gravitational wave community, contributing to both LIGO and Virgo collaborations, also to future detectors. In this talk, I will just focus with ground-based detectors, but Spain is also doing very important contributions to space, to the Laser Interferometer Space Antenna, the Future Instance Telescope, that also this institute is involved, and many theoretical, observational, and instrumental science of research. Contributing to the LIGO scientific collaboration nowadays, there is the Instituto Gallego de Física de Altas Energías, the UIB, and in the Virgo collaboration with Universitat de Valencia, Universitat de Barcelona, IFAI, and this institute as well. So I'm very proud to be here to visit my colleagues here. So what do we do at the University of the Balearic Islands? So we are part of the LIGO scientific collaboration, GEO, LISA, and ET. And I was among the founding members of the LIGO scientific collaboration already back in 1997. Currently, our group is composed of, it's a medium-sized group, 3 faculties, 4 postdocs, and this number is going to grow in the fall, 7 PhD students, 2 masters, and several undergrads. And basically, our research is focused in the analysis of gravitational waves from both binary black holes and neutron stars, and also we are also involved in continuous gravitational waves, and also all the modeling that is required to identify all these events, all these that have been seen until now. One of that will appear during the talk, one of the models called the phenomenological models used for the analysis of all the events, in particular the latest generation has been developed at UIB. And basically in our group, several of us have been leading several of these papers, projects of the last science run, both in continuous waves and also gravitational lensings, test of GR, and so on. So we have a group, as I say, medium-sized group, but extremely active. So since 2016, basically 6.5 years have passed. And what is the status nowadays? Is that in these 6.5 years, there have been already 90 detections. These 90 detections in which we have been discovering basically a full new zoo, a full new families of binary mergers, mainly of families, population of black holes that we didn't know that it exists, and several mysterious things. So there have been already 3 observational science runs. The first one of the discovery that lasted 4 months. Then the second science run, the one of the multi-messenger that lasted 9 months, that joined by Virgo during 1. And then 03, that was supposed to be 6 months, a stop of 1 month and 6 months more, but COVID arrived. And so it became only 11 instead of 12 months long. And now basically all these detectors are being upgraded. And the plan is to start operating again at the end of the year, in December this year, at a much higher sensitivity, all of them. Then there will be another upgrade. And finally, what will be 05, that it will already be even beyond the design sensitivity of these detectors. So basically, we're talking that now we have 90 detections. So we can have easily thousands, and then even more. So that's one thing. We are growing the networks data. They become more sensitive. We will have more events. But also this network is growing. So now we have the 2 LIGOs plus KAGRA plus Virgo. And is it important to have more detections and more detectors? Yes, because then the possibility that one event happens when not all the detectors are operating, well, it happens, I mean, but you would like to have to do coincidences for these transient searches. You would like to have at least 2 sites operating at the same time, or 3, or maybe more, and why more? Well, just imagine that basically at design sensitivity, we have 4 detectors, but just located at 3 different sites. You can still have what we call our blind spots of the network. And if it's Hanford, Livingston, and Virgo, and then suddenly you are, let's say, India, suddenly you have no blind spots anywhere in the sky. And also the localization improves a lot. So it's important to have this network spread around the globe for many reasons. If you want, then I explain more details.
Rather than LIGO India, why don't they try in Australia? They
have
a very strong group.
They have a very strong group. They tried many times, but basically at the time in which this was decided, they were committed to escape. And also there are personal issues, personal egos, fights, and you cannot shout the politician.
Do you think it will change in the future?
Well, I have removed everything of 3G generation out of my talk. I would say the path towards third generation detector is very clear in Europe, is Ancient Telescope. In the US, it's called Cosmic Explorer, but they're basically just a more conceptual thing they are behind. But in Australia, there is a site, there is the Gingin site. They have a very central facility that is very good. Basically, you just will need to grow the arms. And I think that's basically what will be the intentions in the so-called NEMO detector. But NEMO is again a name, a project, there's no funding behind, and you never know. I mean, when Australia failed, basically India said, we do it, and they are doing it.
But it would do much better in terms of localization, right?
Not necessarily, not necessarily.
Okay.
We will also have Japan. So basically the status is that there are many different kinds of sources that can be observed from ground, basically stellar mass sources. And these different sources, for example, we classify them in different groups, compact binary collection systems from ground, basically, that will be coming from either the merger of two black holes, so the first one in 2015, either the merger of two neutron stars, seen for the first time in 2017, or these mixed couples of black holes together with neutron stars that were identified for the first time in 2020. So all these 90 detections, they are just these classes of sources, and most of them just binary black holes. But there are many more things that all these three collaborations, because we are three disjunct collaborations working together, we are looking for. Basically, other kind of transient searches, kind of what we call burst searches, that usually one potential sources will be these supernovae, not as well modeled as these other ones. It could be stochastic backgrounds, either cosmological or astrophysical. I'll tell you just very briefly about it, so I've not seen anything. Or continuous gravitational waves that mostly will come from spinning neutron stars in our galaxy. And this is basically what I'm going to devote the second part of my talk on looking for these kind of sources, like continuous waves coming from neutron stars, either isolated or in binary systems. We don't work alone. Even for many years, we were like a completely isolated group to the rest. Now that we have data and we have observations, we do collaborate with many other observatories. Why? Because all these high energetic cataclysms, all these events, will not just produce gravitational waves, but also they will emit at the same time electromagnetic radiation, neutrinos, cosmic rays, and so on. So basically, it's very important if you have one of these interesting events, if you could have information coming from the different messengers. There's much more than you can get. And this was also initiated, it was a major breakthrough when in August 2017, there was a short GRB that was detected in coincidence with one of our events. This was just amazing. This was amazing because to get all together, let's say we could localize in which galaxy it was happening. We could have the optical counterpart. Then this source was studied intensely all over the electromagnetic spectrum. We could trace out all the kilonova, as you know, and basically the X-ray and radio emission peak after 100 days, and this was detectable for basically a year, and it was followed for basically a year. So it has been a fantastic event in which basically confirmed that binary neutron star mergers is one of the sources of being the progenitors of short hard gamma reverse. They could verify with high precision that gravitational waves travel at the speed of light. It enabled for the first time a measure of the Hubble constant with just one gravitational wave event. and they gave us also more information about Newton's star equation of state, and also with this kilonova event, more information of the amount of heavy metals that we have here in ground, where they are coming from. So all this, the collaboration has been producing by now 3 catalogs. For example, catalog 2 was including the events from the first and second and the first half of the last science run. Then there was a bit increase this catalog. And then in these catalogs, we give the confirmed events from the point of view of the LIGO scientific collaboration, but then we also give thousands of other candidates that pass at a certain pulsar threshold. So we don't classify them as events, but if people want to analyze them deeply, we just tell them there are many more things behind them. So the events that one has seen cover a wide range of masses. Most of them, I say, correspond to binary black holes. The redshift, we have seen events up to a redshift of 0.8. So still we are in the very local universe among us. And basically, in some cases, apart from the masses, we also try to recall which are their spins. And the spins is very important because they can give us information about how to discriminate these black hole populations and provide some information about possible formation mechanisms. And we see that in some cases, clearly there is an indication of this spin. And the last catalog added a few more, and added a few more from the second half of this observation. So all these basically published together, except that we did what we call the exceptional papers for exceptional events. And this is the list that I will go basically one by one of these kind of events, because each of them has a different peculiarities. So I guess you guess it by now, GW means gravitational wave, then comes the year, the month, and the day. Now we'll make them a bit more complicated in the notation. So the first one that keeps our attention, this 190412, it was an unequal mass binary black hole. What is interesting, so the masses of the 2 components was 30 and 8, so you can see quite a difference. And when you have a system that is quite asymmetric, then one knows, according to Giara, basically, that is not only going to be the 2-2 mode, the one we'll observe, but also there are going to be higher multipoles. And this case was the first clear evidence for unequal mass components, and it was a clear measurement of these higher order multipoles. And also what's quite interesting is that we have different waveform models to search for this data and to analyze the data. And the results that we got were very robust against all these model systematics. So even the phenomenological or the models based on EOB, using higher modes and precession, they basically gave consistent results. And what is interesting in this graph here is that if you do an analysis only with using the dominant multipole, so the 2-2 mode, basically, and then you compare the results adding higher multipoles and precessions, then basically you see how the posterior is constrained by including these higher modes and this precession. So that's a case that is quite interesting. Then another one was the so-called mystery merger, the 1908-14. And this was a system that merged a black hole of 23 solar masses with our mysterious object. And this mysterious object is that initially when we analyzed it, it was either it could correspond to the lightest black hole ever or the heaviest neutron star. From my point of view, this is also a black hole. I think, well, in any case, but this was representing a challenge in the star formation scenarios, and this was also representing a new class of binary merger. So for me, this was unclear what it was, and to me, this is also a black hole from my point of view. Then another of these special events was a 1904-25, and this was a binary Nestor star merger. Okay, so the 2 masses, these are totally consistent with the masses of neutron stars. But why is it so interesting, this one? Is because the total mass of the system was 3.4 solar masses. Now, if you compare this 3.4 solar masses together with basically the population or the histograms of the galactic binary neutron star galaxies. So it happens that the mass of this system is basically separated 5 sigma from the mean of our galaxy binary neutron stars. So somehow this is very massive. So this is, as a system together, it's very, very massive. And it could indicate that there is a population of binary neutron stars or peri-binary neutron stars that maybe is invisible to radio pulsar surface. So that's quite interesting. Of course, there is the possibility that one or both components could be black holes. So this is never completely ruled out because basically we classify things so far, or mostly because of the masses. The other one, this is the one that I find it very nice. That was the merger of 2 bodies, 2 black holes, 85 and 66, that gave this 150. So basically anything higher than 100 solar masses is what we call an intermediate black hole. And this is the first time we have any evidence that intermediate black holes do exist. The first observation of them. So this is the most massive gravitational wave binary observed today. The distance is 7 giga light years, so the one at redshift 0.8. So indicates the first clear detection of intermediate black hole, the resulting one. But what's also very interesting is not just this, but these other 2 guys. These 2 guys that are 2 black holes, and basically we know that from the pairing stability supernova mass gap, that basically we should not have models, and what depends on metallicity and depends on many things. You should not be able to produce that easily black holes between 50 and 120. If you want to be easygoing with the models, maybe this could be 60 or 60 something. So basically, well, this case is borderline, but there's no way to explain where this guy is coming from. A possible explanation would be that this guy is actually a 2nd generation merger, that this is the product of a merger of 2 other black holes that have produced this guy and now is merging with this other. And so there is this evidence, and this was one of the cases in which detailed analysis were redone also by our group. And then there are these other 2 guys that are the first 2 that are the first detections of neutron star black hole system that we confirm. These 2. Fortunately, no electromagnetic counterpart was observed. This could be well expected because basically here the black hole can just eat the neutron star before disrupting, so you can get nothing out of it. And this also in our group, they were doing a lot of parameter estimation analysis performed, many of them, or all of them, running at the Mare Nostrum. So this has been
very far, no? 300 megapascals.
Yes, yes. Then we just not do just this. It's just, as I said, we can even do cosmology. And so CDC are standard sirens, and they can measure luminosity distance directly from the signal. Now, if one will have distance and redshift at the same time, then one can just put this information together, as you know, and get information or try to measure the Hubble constant. So basically, we can get information or have the best constraints. We are going to get them are going to be from these bright sirens, like the one that we say, spectacular one, the first that we observe, that have electromagnetic counterpart. We have electromagnetic counterpart, we have the redshift. So 1 to 1, we just equal, get the Hubble constant. Or as the rest that we got are what we call the dark sirens, is that we don't have counterpart, so we don't have information or direct information about the redshift, but still we can try to get more information about cosmology, just comparing with galaxy catalogs and trying to infer cosmology with population models. So basically with one event, well, we could measure the Hubble constant and basically the peak was basically between the 2 ones that are in tension. Our barrow bars are huge, so well, we are there. It will improve. Some people will improve better. Then, as I said, another kind of signals we are looking at for stochastic backgrounds. Stochastic, we have cosmological or astrophysical origin. We have not seen a thing. And there are different kinds of searches that we do, what we call isotropic searches. That is just to see if we see anything, to estimate this background or not. And these are our results so far. And then we hope that when we reach design sensitivity, it will improve. And let's say with O, so this will be O4 and this will be O5. But I think what is important here is that if we start seeing many of these binary black holes, binary neutron stars, or mixed mergers, okay, if maybe we have too many, and maybe there's a background. So some people have been estimating that there could be backgrounds coming from binary neutron stars or binary black holes, and this background could even increase if we include also the neutron stars black hole mergers. So far we are far away from it. The next round we will still be far away from it, but when we go to LIGO plus, so in the O5, well, we could start saying things. That could be quite interesting. We also do look for this stochastic background in different points of the sky. So we look also for the anisotropic, and we try to do math, and again, we have not seen any significance. Now we do a little break. So basically, I talked you a little bit about our transient CDC searches, about the stochastic background, and my rest of the talk, I'm going to focus on these persistent, long-lasting, continuous gravitational waves, a very simple waveform, mostly coming from asymmetric neutron stars, but basically that I devoted my last 20 years looking for them. So when we have a neutron star, and with certain kind of an asymmetry, because this is fast spinning, it produces gravitational waves. And there are several mechanisms for which they can be producing gravitational waves. The first one is that, as I said, there is some asymmetry, or we call it the tiny mountains, not necessarily need to be mountains. And why there could be mountains, it could be due to stresses in the magnetic fields, or could be other reasons, or homogeneity, whatever. So in such a case, it's going to produce a continuous gravitational wave that is going to be at twice the rotational frequency. So basically, this is log, the two frequencies, the rotational one and the gravitational wave. The amplitude of the signal depends on the distance of the source, the frequency of which is emitting, of course, also the moment of inertia, and this deformation, this ellipticity. This ellipticity that properly defined is basically this ratio of these moments of inertia. And just to remind that basically, if for the first detection of a gravitational wave, the amplitude, the peak amplitude was 10 to the minus 21, putting very optimistic numbers, so going at a distance of 1 kiloparsec, not even galactic center, so just in the neighborhood, assuming the frequency of 100 hertz, the canonical moment of inertia, and a very, 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 very large ellipticity, basically we will be talking about amplitudes of 10 to the minus 25. So these are very, very weak signals. But we have the advantage that since they are very long lasting, we just can integrate the signal long enough so that eventually the signal will build more on top of the noise. So we could have a chance of that. This is not the only mechanism. Another mechanism for which these sources can emit gravitational waves is because they have free precession, because the rotational and the precession axis, well, the symmetry and the rotational axis are not aligned. And in that case, basically, the gravitational wave's frequency is going to be more or less at the rotational frequency plus minus the precession, or at twice, or both. Another of the mechanisms is that, well, we have in the Electrostars, we have the crust, but they have the interior, basically fluid interior, then we have also another solid core. So basically, the fluid that makes most of the star can have long-lasting oscillation, like the arc modes. The arc modes is one type of them. Basically, it's a kind of instability due to the rotation of the star. And if the gravitational waves are produced due to arc modes, then the signal is going to be a 4/3 gravitational frequency. And of course, the amplitude is going to depend on the arc mode amplitude. And again, we are talking about extremely weak signals. Not just that, these sources can be alone, isolated, or in binary systems. And the typical thing is like if they are in a binary system, they might be accreting matter from their companion. And if it's accreting matter, there is some kind of deformation, and then we have some deformation. Because of that, we emit gravitational waves. So, and at that case, we respect the signal to be more or less at twice the rotational frequency. So accreting is going to power gravitational waves. And there is a kind of a Tor balance theory in which somehow the accreting spins up the star and gravitational waves slows it down. So there's a kind of an equilibrium. And that's also a bit complicated because if it's eating matter, it's accreting matter, then the frequency is not going to be stable. It's going to be wandering depending how is the accretion rate. So why I'm not very interested in continuous gravitational waves? Well, because studying this, if we get information from gravitational waves from these systems, we can get a lot of information about the interior structure of the neutron star. We can get information about their properties, about the masses, the spins, the ellipticities. We can get information about the nuclear equation of state. We could discover other exotic states of matter because we assume that they are form of neutrons, but they could also have quarks in their interior. They could be very exotic. Of course, it's very interesting to do multi-messenger studies, and also try to check if there is this phase lock between the electromagnetic waves and the gravitational waves. They can be this with these long-lasting signals. We could also do tests of GR. So we can do many things. It's not crazy because we know that these sources exist. The signal is going to be very weak, but we have the sources already in this galaxy. So we know if we go to the catalogs that already there are more than 3,000 neutron stars that exist, that they are in the catalogs, in the existing catalogs. And we know that up to 1 billion of neutron stars are supposed to exist in the Milky Way. Even if I just consider the millisecond pulsars, we know that of the order of 40,000 millisecond pulsars might exist. And of neutron stars, most of them are going to be electromagnetic wide. So this is basically from the catalog, the period and the p dot of all the non-pulsars. And our detectors are going to be sensitive, let's say, from 10 Hertz on. So these are the ones that are in the LIGO band, and these are going to be invisible. So it's quite pity that the most majority of them were not going to be accessible for the time being, maybe for the T and E, but not much more. So just a few of them, the millisecond pulsars, are the ones that we could in principle target. As I said, well, the expected maximum frequency is going to be below the 2 kilohertz. I'm not sure if it's the fastest rotated pulse is around 700 hertz. So up to now, the gravitational one will be at 1.5 kilohertz. The source we are searching is in our galaxy. So we are talking of distances smaller than 10 kiloparsecs. And this here, the ellipticity, is a parameter that is largely unknown. Theoretically, we know that the maximum value, the maximum of the theoretical for a standard neutron star is going to be 10 to the minus 6. It could be a bit higher for exotic equation of a state or for exotic matter. It could even be up to 10 to the minus 4. But the most realistic ones is that for many cases it's 10 to the minus 9 or whatever. So
my question, can you marginalize over the electricity? Like integrate this with some probability?
What we do is the concept that I will explain now. I hope it's coming now. That is like this, is that at least for all the pulses that are in the catalogs, what we can deduce is that we can we have the p and the p dot, so we have the frequency and the derivative of the frequency, and therefore we know how much energy is lost as rotational energy. If we could assume that all of them behave like gravitars, so that all the energy will be powering to gravitational waves, and then we know how much energy is emitting gravitational waves for a given electricity. So basically, if you say that all the rotational energy is lost into gravitational waves, you can equal, and then you can try to deduce what will be the upper limits, both in electricity and both in, and then when you know the electricity, you go down to the previous equation, and then you get the maximum of the speed of the amplitude of the signal. So this is one can do, and one can do it for all the non-pulsars, assuming that you also know the distance, etc. And basically, these are the kind of draws that have been there forever. of all the non-pulsars, which will be the amplitude in H0 and the spin down ellipticity. But that doesn't mean that this is the H0 and this is the ellipticity. This is the spin down upper limits. So this is the kind of things we do. And the kind of things when we target, so all the pulsars that are narrowband, we target them. And then this will be their strain amplitude, assuming this that they are gravitars. Then assuming that we do integration of the data for, let's say, a full year, and that we do it with the best data analysis method, the best filtering, match filtering. So a coherent integration for a duration of 1 year. So this is the what will be the design sensitivity curve for advanced LIGOs, that will be O4 and O5. So basically you see that most of the dots are below, so clearly no chance to see any of them, and some are on top. But that doesn't mean that they are just this is the amplitude. They are, it could be also several orders of magnitude below. So actually we have no clue, even we know we have lots of potential sources. We have no clue if we are going to see them, when, or which is the sensitivity of the detectors that we need to actually see those signals. So this is a bit sad, I would say. So basically, we need to advocate for a better modeling of neutron stars, the formation, in order to enhance the science case. These were the results just for analyzing O1 and O2 data for the 222 non-pulsars that were in the range. And at that time, the spin down, so these limits were beaten by 20 pulsars, and the most stringent upper limits on the strain was 10 to the minus 26, and for the ellipticity, 6 times 10 to the minus 9.
Any data or crap, are they in the blind spot of any detector?
No, that's
So
okay.
we should see them.
We should see them. Crap is around the 60 hertz, and that's the power of in the US. It is a bit separated. You don't have to worry too much. So we know that they exist, and the signal in principle is very boring. They are emitting a almost monochromatic signal. It's not really true. It could be some signal evolution. As I said, there's already some frequency derivatives, but that's how the signal is emitted at a neutron star. But when we receive it in our detectors, and when we receive it all around the year, the Earth moves. So this signal is Doppler shifted, and it's Doppler shifted due to the movement of the Earth around the Sun and the daily rotation. So basically, we have an annual variation of the frequency that multiplies the frequency for 10 times to the minus 4, and the daily variation that multiplies by 10 to the minus 6. That if the source is isolated. If on top the signal, the source is in a binary system, then one has to add the modulations to due to the motion of the source itself. To make it more complicated, our detector does not have the sensitivity in all the equally in all the sky, but the detector moves. So maybe the signal for during 10 minutes is in a blind spot, but 10 minutes later is not anymore. Okay, that means that since this rotates, the signal is also going to be amplitude modulated. And the amplitude modulation and the frequency modulation depends on each sky location. It's completely different. And there are also more effects. So these boring signals makes it a very interesting problem. And this very interesting problem, we do different kinds of searches. So basically, this is how we classify the searches for continuous gravitational waves. Some are searches that are very sensitive and computationally very cheap, and some other ones that we have very poor sensitivity and are very costly. So the ones that I am devoting my life are these blind, the most expensive, but the most promising ones. So what are these? Target searches. So basically, we will go to all these known pulsars in catalogs for which we know the sky location, and we will assume that the gravitational wave signal is locked to the electromagnetic one, so for all pulsars. So we will have perfect templates. They are going to give us ephemerides. We will do perfect thing and simple match filtering, very easy. But we just have a few sources that are already in the catalogs. Then we could do narrowband searches. That is the same for the same non-pulsars. We will know the sky position. What we could do is to relax a little bit this coupling between the gravitational wave and electromagnetic signal. So we let a bit of freedom in these searches. So it's not just a one template, but several templates for each of these targets. So this costs a bit more. In other cases, for things that we know in catalogs, for example, supernova remnants and so on, things that we know that are in certain sky locations, interesting sky locations, but we have not found the pulsar. So we don't have the information, electromagnetic information. So we don't have information about the frequency or the frequency derivatives. So basically, we are targeting neutron stars or potential neutron stars with all the ephemeris. Or you could even do more exotic things to search for boson clouds around known black holes or others. And the most expensive ones is that you know nothing. But I know there are many sources out there. So basically, what we are doing is to scan all the possible positions in the sky for all possible frequencies and all possible spin outs, either isolated or in binaries. Of course, well, as you know, we have not detected any signal yet, but already the observations we have obtained already give interesting information, statistical information. And now I will try to scan fast to the results obtained in these different categories. So basically for the target search, so we're trying to constrain equatorial electricity, in particular for millisecond pulsars. In this paper that was using all the data up to the first half of 03, and basically target 5 radio pulsars. And this was in this paper the first time that that the spin down was constrained for millisecond pulsars and constraining electricity below 10 to the minus. That was quite interesting, and you see there are at different frequencies, the ones that we are targeting. Another one is this variant pulsar that is also known as the big glitcher, because it's a pulsar that is very young and it glitches a lot. A glitch is like if you happen like an earthquake. It's an X-ray pulsar with the largest spin down luminosity. And this one we searched it both at once and twice the spin frequency. And it was for the first time using this data that the spin down limit was also beaten by more than a factor of 2. So that we know that gravitational waves would account for less than 10% of the spin down budget. And therefore the electricity would be smaller than this quantity here. For the same pulsar, I could suggest like, oops, maybe it could be our mode oscillations. And therefore research was also done for our mode oscillations. And this time we searched between a different frequency band. So these 4/3, but the 4/3 with some flexibility in order to deal with some equation of phase uncertainty. And again, we excluded the possibility of these modes. And with the latest data for all the ones in the catalog, so 236 non-pulsars have been traced. And up to now, for 23 of these pulsars, we have already beaten the spin down limits. And for Kappa and Vela, we know that we have beaten it for more than 120 times. So basically, sadly, almost all the results that are below the spin down limit have electricities that are very large. So they still could be much below. Some of them are quite interesting, for some of these millisecond pulsars. We also do narrowband searches, as I said, and this is the results that have been, it's going to be an 8J, that's already accepted, for 18 non-pulsars. And for these 18 non-pulsars, also for 6 of these targets presented several glitches, in particular presented 9 glitches in the total. And basically we also didn't see a thing. And also we did this glitch. When a glitch happens, suddenly it's like the rotation frequency can change and spin up. The emission also grows and then it relaxes. And then it's like it's a different kind of searches because are long duration searches, not transit but long duration, but also not completely continuous, because one can search for this kind of signals after a glitch that could last hours or maybe months. So this kind of searches has been done also in our group, where there is also leading the glitch searches. Then accreting millisecond rate pulsars. In this case, one searches at frequencies at 1, twice, and at 4/3 rotational frequencies. So this was done for 20 of them. And we put for one of them, the lowest ellipticity was 10 to the -7. The amplitude of the R mode amplitude was a bit more than 10 to the -5. And this is quite interesting. Also in this directed, so directed means we only know the direction, but then we have to scan among the different frequencies. So we scan supernova, interesting supernova remnants. So the location is known, but not the rest. And we search several of them. We have several algorithms looking. And what's quite interesting is that in some cases, we can surpass the limit of 10 to the -6 for the ellipticity, or this 10 to the -3 for the amplitude of the R modes. We also look in the center of the Milky Way, same story. We have been suppressing things. See, we have searches between 10 Hz and 2 kHz. Also, the brightest, the most luminous low matrix range binaries is SCOX1. So we also do a very broad searches for it, and different algorithms. And these are basically the different results that one obtains. And still, we don't have all the results from all the algorithms. More are going to come up. And basically, all these later ones are already presenting a large computing challenge, because just to target one of these, or say, or one of these supernova remnants, if you want to do it with a coherent search, much filtering, basically you have to put a grid. You have to search over different values of frequencies and frequency derivatives. And the grid that you have to put should take into account that you don't want to mismatch, say, more than half a radiance in the templates. And if you start constraining this, that means that it gives you more or less like an educated guess of the sizes of your grid. And this T-coherent is the coherent integration time that you can do for your search. So the cost of a search in these cases, if one has to search up to second derivatives, it's going to have a cost that is this time coherent to the power of 7, already knowing the position. So this is very expensive. And this increases with young objects, in which you might need to put further derivatives. So basically, for an old case, like I say, maybe you can do coherent integration times up to 10 days, not full year. The thing comes more dramatically if one does all sky searches, so that you have to scan not just frequencies and frequency derivatives, but also the sky locations. So, as I said, the modulation coming from the Earth was 10 to the -6, and for the Earth orbital motion 10 to the -4. So if we have a signal, let's say, well, if I do a coherent integration over 1 year, my frequency transform resolution will be of 30 nanohertz. And if I have a source at the kilohertz, this is going to spread over 6 million bits in an ordinary Fourier transform. So it spreads a lot. So I have to apply, you cannot just do Fourier transform, so I have to do funny things, as I say. And I also have complications due to the antenna pattern, but also had some advantages. That for this kind of sources, in order to detect something, I just need one detector. All this mess with the Doppler shifts and all these things, is like a detector. It's like it behaves like an array of detectors because the detector moves. So it gives excellent localization. So it gives precise direction of the source. Too much precise direction of the source. So to search continuous waves, if you know which is your target, it's something very easy. It's cheap. It's not any challenge, because basically you will analyze the correlations of the known waveform with the data, and that's it.
What's the measure of resolution depth from the ear of orbital motion of the Earth?
A lot, because the number of sky locations that I can distinguish goes like this: f squared, T coherent squared. So So, but blind searches, all the sky searches, has a problem of that. But apart from frequencies and frequency derivatives, the number of sky locations goes with the frequency square. So if I just look for only first derivatives, computational cost scales like time coherent to the 6th power or more. So that basically tells me that coherent integration time I can only do for a few days, no more. I would need a lot of computing power. But on top, there is a problem. There are so many templates. The number of templates is just brutal. It could be 10 to the 16, 10 to the 20, 10 to the a lot. If I will be do coherent integration, it has a problem. That if I do too many templates, just even if it will be Gaussian noise, I will be getting events at the 6 sigma level. And in real data, this is going to be producing even 7 sigma artifacts. So in whatever search I do, I have a lot of artifacts that I need to analyze carefully and do follow-ups. And because of that, if for a known signal you will put a certain false alarm threshold and say, okay, I believe it or not believe, just because of these too many templates, I have to put for the same sensitivity, I have to put the threshold much higher up, and therefore I'm much less sensitive. So full coherent searches are prohibitive, are not possible, are not at the end not the most sensitive. So we have to find other strategies. And this is what we do in our group. Our group is planning to develop other strategies to make feasible these kinds of searches at a very competitive sensitivity. So all these methods, coherent methods, is that you take the full data, you cut it into pieces, you will do coherent searches for each piece, and then you try to put together all this information. Imagine that you have just done Fourier transforms. One possible thing is to trace signals over time at different frequencies. The sensitivity of the searches, the signal to noise ratio. Well, it depends on the amplitude of the signal, the level of noise, the coherent integration time, and how many segments. The more segments you put, the less, in principle, less sensitive you will are. But you can do much faster. The grids can be much more coarse, and suddenly you can make the grids feasible. There are many kinds of these methods. Some add normalized power. I do half transforms. That is basically I add ones and zeros with some weights. Some other ones do something called power flux, that is basically to add power, but also with weights. And for many years, we have been comparing these methods. Of course, if you add power, it's better than to add ones and zeros. So some methods are better, but half, that is what I work on, it's very robust. Because when you have noisy signals, it becomes extremely robust thing. But here, for example, is another one that some comparison. We do lots of non-data challenging, comparing different methods before we apply it to know who will be running on the very large computers. So this is a time in which instant home was still part of the collaboration. When we are in bands of very well-behaved data, the ASNL home algorithm or pipeline was the most sensitive one, even one very computationally expensive. And the second one was might have transform. When you have noise, basically the one that was keeping at the same level of basically sensitivity is the half, while the other ones suddenly get worse. And what is also very exciting is the parameter estimation, which is the error that you get just from these initial stages. And the half transform that we have been working gives very good resolution in the spin down and also in location of the sky. So what is this? You tell me how much you want me to talk, because I can explain what half is and then I can go very fast. Okay, so I will explain this half transform. That is what I've been working, I would say, for so many years. It's a very robust pattern detection technique. And basically I use this half transform. I mean, you might recognize that I just put here a Doppler formula to trace, to find patterns in the time frequency domain in my data. So given the velocity, the sky location, and the frequency of the signal, I can just try to find which frequency will be received at the detector. And the intrinsic frequency of the signal maybe varies over time due to the different derivatives. So basically, this formula here is going to describe different patterns depending on the sky location, f and f dot of the signal. So the idea is to get the data, break it into segments. The very simple way is just to do a Fourier transform of each segment. So then I will be converting the data into spectrograms. Then in the spectrograms, I can select points that crosses a certain threshold, and give a full seminar on that. And then I will have like a random distribution on ones and zeros. And on these ones and zeros, I can try to search for patterns, because if there is a signal present, maybe on a certain pattern, there might be more ones than before, and in a random one. So our idea is that we have these graphs, black and white, ones and zeros. And then for each point in parameter space, we search for this pattern, and we get histogram, we get number counts. And you can put a threshold and the number counts, and then these are your selected candidates. This is very simple. Then we put weights, because depends if the data is better behave or less behave. We also can put weights at different times, depending if the detectors were more sensitive or less sensitive, depending on the antenna pattern in different scale locations. So that's basically the basics of half transform. And then there are different implementations in different flavors. So the one I work is called SkyHub. And because it's a technique that has been used for many, many years, from the initial LIGO S to run, and it's optimized template placement. Currently, we are even using GPUs to run GPUs. And now we are implementing even machine learning techniques. And basically this method of implementing, so now we know what we want to do, what we want to add, so we want to implement in an algorithm very, very efficiently. And then one realizes that looking at the Doppler formula, basically, there are like correlations in the sky, and my ones can be compatible with circles in the sky in this time frequency plane of the data. So I can study very large sky locations, sky patches at once, at different times, and then I have my partial half maps that then I can act in different ways depending on the frequency evolution of the signal, and then very cheaply or very efficiently I can compute it. And this has been used in many searches. And what is interesting is that there is another half implementation by the group in Rome that's called FrequencyHub. And for the O2 search, they cover only until 1 kilohertz. We went until 1.5 kilohertz. Remember the cost goes like F squared. And we spent 2.5 million service unit hours of computing power, while they cut to cut much earlier were already at 9 million units. So it's the cheapest search, basically at a similar sensitivity. Then when we do the searches, we have to follow up things, and then we have to start doing coherent integrations for longer and longer time. So we do comparisons and different things. This is involved. It's involved, I will skip this. And suddenly, one important thing is like about these high frequency pulsars. Basically, for pulsars in the catalog higher than 10 hertz, there are 458 in total. And basically, half of them are in binary systems. So if the searching for isolated pulsars is very complicated, even more is going to be in binary systems. For isolated, we only have to search frequencies, frequency derivatives, and the sky location. In binaries, we will have to add projected amplitude, period, time of ascension, eccentricity, argument of the periapse, so many more dimensions. We can simplify things is that basically one checks which is the spin down of these pulses in binary systems is very low, so we could ignore derivatives. We could even assume they are in circular orbits, and then we can reduce the problem to a 6-dimensional parameter space. And one of my students, basically half of the PhD was devoted that this method that we use is a scat half, but then we look for traces depending on the spin down. We could just look the same, and basically when we have the maps done, just look for the orbital Doppler. And this is a nice implementation. It was done running on one of the Barcelona machines, not on the rest. And basically we managed to have the best search ever for many, many years. It was published in field regulators. And now we did then the most sensitive search for the collaboration using the O3 data. And what was interesting is that when we have this upper limit, we didn't see a thing, we could also constrain the electricity at different distances. That already got interesting. So these are kind of things we do. Another thing that we do, I'll go extremely fast, is that we have outliers. So we have to find ways to beat our candidates. And then we do coherent integration time for longer times. but then we check if there are jumps in how this, what we call F statistics, that is a quantity that we measure suddenly increases, is that decreasing steadily, or if the signal to generation one detector, it gets higher than the multi-detector one, and this should be the highest. Then we also study correlations in parameter space. Basically, when we have outliers, it's not that we have one, usually we have thousands, millions of them coming. And that if you have a signal, we will be triggering many templates. And if you have noise, also triggers many templates. So this have to be grouped somehow. So we have to be clustering events, group them, in order that when we do follow them up, we can rule them out or continuing to narrow band the parameter space. So, so we did a way to group clusters, we improve things, defining distances in a different way to put things together. Then when we follow up things, we have like a little box around our candidate that we have to put a finer grid and look with more sensitive methods, not just these coherent searches, but others. And these are extremely costly. So if initially we were starting by doing grids, then we start moving into Markov chain Monte Carlos, and then also developing hierarchical searches of Markov chain Monte Carlos, in which one keeps increasing the coherent integration time and reducing every time the volume in parameter space search. And then even when we have finished this hierarchical Markov chain Monte Carlo increasing and we have reached the coherent integration time of a year, you might still have surviving candidates and you still have to decide if that's a signal or that's noise. And then we also have been developing things called like the bias factor when we don't know the exact distribution. We have to model somehow the distribution of the top candidates that we have been recording and trying to distinguish if we are talking about signal or noise. So these are the kind of problems and the kind of searches that we do. In our case, in our searches, it was not the most sensitive one for the all sky in the last data, but in the data, we also inject signals and we search, and the hardware injected pulsars, the ones from the algorithms that we were using were recovered with an extraordinary resolution, basically in frequencies, frequency derivatives, sky locations, and so on. And these were like the last results. This is not yet, it's out, but it's not yet accepted, this paper, of the searches doing isolated all space searches, in which we cover a quite broad frequencies and frequency derivatives. And this red orange here was the UIB pipeline, the SkyHub, that basically at the end was the most sensitive case in most of the cases. And not just that, I will basically finish that we don't only look for these continuous gravitational waves. They could be things like after a binary neutron star merger, you could try to look for the post-merger signals. The post-merger signals that could be very short, or could be last hours, or could last several days. So these semi-coherent methods can easily be adapted to also try to search for this kind of signal that will vary the frequency extremely fast, and the amplitude will also drop extremely fast. So basically the algorithm that I went very, very fast to explain of the half transform, you can keep adding ways to account for these kind of things. And these were also used. We adapted our search pipeline to also look for this kind of signal. Since I got the drone, but my hour by a lot.
Thank you very much for the compliment.
And if you have questions, I'm here also today and also tomorrow. Okay?
We were talking about the black holes in the forbidden zone, and we were giving as an example that this might be a secondary merger. Is there by now a robust theory predicting how many of those one should expect? Or...
No, and I don't. So now one left, because he could just come and tell like, oh, maybe they were primordial, heavy primordial black holes. But I can discuss with him tomorrow. I mostly believe that the one of 85 could easily be a second generation merger, or this is opening the door for more questions like some of these models that we are using are not correct. Also, I mean, these models have a lot of parameters. You suddenly change these parameters in these models, And then if the gap was between 50 and 120 was forbidden, you change some of these parameters, and then the gap gets small. This 50 comes 60 or almost comes 70. So the other one was like okay-ish, borderline okay-ish. And Carlos is not here, but as I said, there are more continuous wave signal because we look for continuous waves. I don't care if they are neutron stars, they are, well, they care if it's isolated or in a binary system, that I care because the signal is very different. But which is the mechanism that produces this continuous signal? I couldn't care less. Another you could have actually primordial black holes of asteroidal mass. Just by doing the spiral signal is going to produce basically a signal that is monochromatic in our band. Or you could have these axion clouds, boson clouds around the black hole spinning there. That is also going to produce a continuous signal. And now basically we do the searches. We interpret them as neutron stars, putting limits on the neutron stars, but then you can also interpret it in different ways, and then you can try to put also limits in other interesting things concerning that.
In the beginning, you were also discussing this one event where an electromagnetic counterpart was seen. And if I remember correctly, all the theories said there shouldn't be any.
No, wait. If there is matter involved, you have a chance to have electromagnetic counterpart. Okay, so in the case of these two neutron stars that merge, you expect to have electromagnetic counterpart. Now the first one, I mean, nature has been always fantastically nice. 2015, we put the detector on and you have a fantastic 10 to the minus 21 signal, completely clear with high masses and so on, with a beautiful trace. I mean, I would have expected all my life that the first signal is going to be something that you are not sure, and a nasty one. And 2 years later, basically was at the same time Fermi gives the alert, and the people in the detector was like, ooh, what in one detector they say, oh, what a nice trace, and then the other detector say, oh, what a beautiful pitch, and then they have to remove. Then it was fantastic because it was like people even talking on the phone, hey, we have the electromagnetic counterpart. Hey, we have a gravitational wave, and then it started to think like, oh my God. Then you have to wait. You have to wait until 9 hours later that was back in Chile, and to do evolutionize the world basically. We could localize it extremely well, and because we could localize very well, they could find the optical counterpart. Now, in the other cases that have been neutron star mergers, in the other confirmed ones, they were not the detectors operating or whatever. The sky location was so poor. On top, this one was particularly close, very close. So it was very close, and we could localize it very well, and we can tell the electromagnetic counterpart easily. So then we could do fantastic science. I hope this gets repeated in the future, but it has, with them, we have very little number of other neutron stars now. The other ones were having sky localization that was extremely poor. Now, when you have mixed a black hole and a neutron star, what do you expect? Well, you could or you could not have an electromagnetic counterpart. That depends basically on the masses and the mechanism of how it has been. I mean, has the neutron star been disrupted before it has entered into the black hole horizon or not? Because if it enters first the horizon and then it gets disrupted, you're blind. Another thing is, where is this happening? Is it basically in a place that is very lonely, or is it in a very dense environment? Because then maybe you also have accreting matter around. So next round is going to be more exciting.
Okay, any other question? If not, it's time to speak again.